Hello and welcome back to Calculus 1, section 3.7, the chain rule. One of the most frequent derivative taking techniques, because this is the way to take the derivative of the function composition. You know, when you plug one function into another, well, that's this. How do you take the derivative of sine of x squared? How do you take the derivative of e to the x squared plus 3? How do you take the derivative of sine raised to the whatever, third power or fifth power? So these are the things that we are going to address in this. And most of your derivatives in the future, not just Calc 1, but Calc 2, Calc 3, differential equations, and then your engineering and economic courses and everything else that uses derivatives, most of those derivatives will be the chain rule. So, oh, thank you. So now, why is this taped backwards? Anyway, so what we are going to do is we are going to take a look at something very, very basic first, and that is function composition. So you are familiar with the fact that if you have, let's say, f of x equal x squared plus 3x, and you have g to be, let's say, square root of x, you can make function composition as f composed with g of x, which means that you will plug a g into f, and you will get square root of x squared plus 3 square root of x, which is x plus 3 root x. And that is the function composition. So that is the function composition. Now, what are we going to do with this? Well, we compute, right? But how about g composed with f? That's g with f of x plugged in. That's going to be the square root, and instead of x, I have to put x squared plus 3x. So my goal is to, now in this section, find the derivative of something that looks like g composed with f. Something that is not a basic function, but a combination of other functions, which is what we in this case call function composition. So, say that you have to take the derivative of x plus 3 squared. Well, the only thing that you know now is to actually square the binomial and then take the derivative. So you can do it, right? It's not a problem. It's going to be x squared plus 6x plus 9, and then when you take the derivative of this, it's going to be 2x plus 6, and you're good to go. But now I'm going to make this problem more interesting. d dx x plus 3 raised to the 217. Go ahead, FOIL, I'll wait. Who gave up? All right. So clearly you will not be foiling this. It's 217 of these. So there has to be a way, right, to deal with this. And there is. It's called the chain rule. If you look at this problem, it consists of two functions that are plugged one into another. There is the outer function, the outer shell function, called f of x. and that is x to 217. And then there is the inner function g, which is x plus 3. So I am clearly able to decompose this composite function into two functions and take a look at those two separately. Now the question is, what would be the technique for the derivative? Now, yeah, go ahead, do your limit thing. See you next year. So here is the formula which you are going to memorize. This is known as chain rule. And then use it in all of these situations when you have composite functions, derivatives of composite functions. So the derivative of function composition f of g of x, so the derivative of that is the derivative of the outer function with g plugged in times the derivative of g. Chain rule. So that's what we have. I could have used the original notation that you are used to, which still gives us the same. So, all right. So now let me use this formula on our new problem, which says x plus 3 raised to 217. So this is what I'm going to do. I know that the outer function, f of x, is x to the 217. And the inner function, g, is x plus 3. So what I'm going to do is I'm going to, in my head, in my mind's eye, I am going to replace this with x. And look what I have. I just have to worry about derivative of x to 217. And that's very simple, right? You drop 217 in front and subtract 1 for the exponent. So you would answer 217 and then have this crazy x raised to 216. Right? That would be the derivative. If this was just x to 217, your derivative would be 217x to the 216. Are we all 100% clear on that in this classroom? We better be, right? So if this was not x plus 3, but just a single x, taking the derivative of that would be a joke, because we know the shortcut rule. But it's not x. It's this composite function. So you know what? Just leave the composite function there. And now times g prime, which is 1. And the whole thing is just 217 x plus 3 to the 216. And that's your first chain rule. So this part over here is the derivative of outer function with the inner function still plugged in. And this over here is the derivative of the inner function alone. And this part over here is called the chain. We are going to do, without exaggeration, about 5,000 problems tonight on this. You really must know this. Let's go and take a look at another example. Let's take derivative of sine of x squared plus 2. All right. We start by figuring out the outer function. So please help me there. That's your pre-calculus 1. What is f? Sine x. It's the outer function, sine x. And what's g of x, the inner function? X squared plus 2. So this is the time, if you have issue with this, to stare at this and make sure that you can put these together. Where G plugs into F, you see that X of F replaces with G, and you have the mess we had in the problem. So this plugs in for X, right? And you get that. So your job is to learn how to decompose. That's your job. Okay. So what are we going to do? Well, let's take the derivative. What is the derivative of sine x? Cosine x. But remember that when I take the derivative, I have to keep g plugged in. So cosine of g, which is x squared plus 2. Times, and now the derivative of g, 2x. Again, the first part is the derivative of f with g plugged in. Second part, derivative of g alone. And that's the chain. Now we just make this pretty. Good. Let's take a look at another one. How about the derivative of cosine to the 5th x? What's f? What's f? What's g? What's f? X to the 5th. And what's g? Cosine x. So, we take the derivative of x to the 5th, which is 5x to the 4th, but we can't put x, we have to put cosine. So, 5 cosine to the 4th x, that's the outer derivative, times the inner derivative, which is derivative of cosine is, very good. So the whole thing is negative 5 sine x cosine to the 4th x. Cosine x to the 5. What's f? Nice. That was g. Yeah. See how they switched? I just moved the 5, yeah. But then the first problem has 5 cosines that multiply each other. The second problem has 5 x's that multiply each other. Write it down if you have issues with the notation from trig course. The top problem has cosine times cosine times cosine, right? 5 times. So it's cosine multiplies itself 5 times. Where on the bottom you have 5 x's that multiply each other. So be very careful with the notation as you go on. Now you will see it's a vastly different answer. What's the derivative of cosine? So we have negative sine x to the 5 times the derivative of the inside, which is 5x to the 4th. So the whole thing is negative 5x to the 4th sine x to the 5. As you can see, has nothing to do with what you had before. So please study these two examples in particular, because the same rule with the 5 on the exponent goes for sine, cosine, tangent, ln as well. All right, ln as well. So you really need to start these guys as two examples that complement each other. They're very different. They look so similar. So that's that part. It's just, doing 5,000 examples. That's all it is. 5,000 examples. The derivative of the outer function, the derivative of the inner function. Now, before I move on, over here, as I said, if I think of this cosine as a big fat X, then you can see in the answer that something that was x to the 5 becomes 5x to the 4th. Now that x is replaced by cosine, and I can unveil over here that x is also cosine. In the next example, the derivative of cosine is sine. So the derivative of cosine is sine. You can see it right there. With the same function g plugged in. I love it when it kicks in every time. It's awesome. E to the 3x. What's the outer function f? Now the air conditioning is on, so you have to really scream it out. E to the x. Good. And what's the outer inner function g? 3x. Good. So what do I get here? What's the derivative of e to the x? E to the x. So I have to copy e to the 3x, right? Times, and what's the derivative of the exponent? Is? What's the derivative of g? 3. So the whole thing is 3e to the 3x. You remember that you learned this as a formula? You had to memorize it, right? So let's now prove that formula which you had to memorize. What is the derivative of e to the ax? Well, the outer function is e to the x. The inner function is ax. Whatever that a is, whatever number. So the derivative of e to the x is e to the x. The derivative of e to the ax has to be e to the ax, because it always stays the same. But now times the exponent. Only e to the x goes into e to the x. Any other modification, well, something has to change. So times a. And you get the formula which you were supposed to memorize, that the derivative of e to the ax is a e to the ax. So now I'm going to ask you to confirm the formula for sine ax. It's the same as e. Let's see. So do we all have solution for sin x over here? Would this be a good name for a medication of some kind? Sin x? Has to have an x in it, or z, otherwise it's not good. That's why aspirin doesn't work. It doesn't have z or x. It's garbage. Hi. Has to be a serious. All right, so what do? We take the outer function, which is f, which is sine x, and then g, the inner function, ax. So the derivative of sine x is cosine x, but we have to use g. So cosine of ax, put this in parentheses if it makes you happy, times the derivative of the inside, which is a, so you get a cosine of ax. Good. And this is something that I asked you to memorize, but now, yeah, you don't have to anymore because you have a method to deal with it. So if I ask you what is the derivative of cosine of 8x, what would you say? Negative 8 sine 8x. Good. Nice. All right. Let's take a look at some of the exercises that book believes you guys should work on. There's always something. The book is not working. There we go. Oh, beautiful. I completely forgot about this. Alright, so let's go. Square root of x cubed minus 2x squared plus 9. Do it. What's the outer function? Square root of x. And what's the inner function? The mess. Good. So f is root x and g is, who came up with this? Yeah. So what's the derivative? We start by the derivative of square root of x. And that is 1 over 2 square root of x. We don't put x, we put g, and g is the mess, right? So it's 1 over 2 square root of the mess times the derivative of the inside. So what is the derivative? Very good. 4x, good. So now we just put this together on the same, so 3x squared minus 4x divided by 2 times the square root of x cubed minus 2x squared plus 9. Again, this part is the derivative of f with g still plugged in, and this over here is just the derivative of g, the inside, and you multiply them. So the derivative of square root of x is 1 over 2 root x. That's what the derivative is, which is the reason why this looks this way. So they have some interesting examples in the textbook. How about e to the square root of x? Go. Ready? What do you have? Very good. So we start with f of x is e to the x, and g is root x, okay? Two root x, not squared, 2 root x. All right, that's it. That was problem 14 in the textbook. The ones up there I made up. Ooh, nice. What's the derivative of sine x over 4? Right. You know that it fits the formula of AX, where your A is a quarter? It's a one-step problem. You already memorized the formula for it, so it's 1/4 cosine x over 4. You move along with your life. What's the derivative of e to the negative x squared? So what's the outer function? Very good. And what's the inner function? So, for the derivative of e, we copy it as is times the derivative of the exponent for a total of negative 2x e to the negative x squared. So, observe that in every example, when you take the derivative of the first part, g of x stays the same. Alright, so now I want to write some other stuff so we can understand this better. So here is another time. So d dx of the function composition is the derivative of the outer with g plugged in times g of x. prime. Now, what I can do is I can say over here, what is the derivative of f in respect to g? In respect to x. Right, that's what we're looking. So for this one, it's actually, this is the derivative of f in respect to g, and times this is the derivative of g in respect to x. Did this make any sense? If you look at this, I want to take derivative with respect to x. Oh, I don't need the prime in there. Kill the prime. You see this prime over here? I'm killing it now. Because this is actually the second derivative now. Because you have one prime, that's the one derivative, and you have d dx outside. That's doubling up or notation, right? So it's like a second derivative. So I'm erasing the tick mark. I don't need that. Alright, so what do I have? Look, I have the derivative in respect to x of f. Well, there you go. The derivative of f in respect to x is, now what is this? This is the derivative of f in respect to g times the derivative of g in respect to x. Are these two sides in balance? Are these two sides in balance? Of course they are. df over dx is equal to df over dx. That's what the chain rule does. Right? It's like you eliminate the middleman. Alright? Now, this is the way to understand the chain rule using Leibniz notation. So the derivative of f in respect to x is the derivative of f in respect to g times the derivative of g in respect to x. And this is the same stuff, still chain rule. Just different notation from what we're used to. All right, more problems. Let's make one up. How about the derivative of 1 over 4th root of x squared plus 3? We need to decompose. Yeah, but there is a step before that. Before you do your F and G, what's the step before? What do you think? We have one on top, so we don't need quotient rule. If we had some kind of x upstairs, then yeah, we have to use quotient rule. But in this case, we just use basic algebra to rewrite this into x squared plus 3 to the negative 1/4. So now your f is x to the negative 1/4, and your g is x squared plus 3. So what do you have as a derivative? You have negative 1/4 x to the negative 5/4 when you subtract 1, and then times the derivative of the inside, and the derivative of the inside is 2x. So what do we have when we combine all of this? Oh, whoa, hold on. This over here, I lied. We need to have the x squared plus 3. So what do I have? 2 and this cancels, so it's negative x over 2. Right? 2 and 4 cancel. So you have x over 2, negative x over 2 times x squared plus 3 raised to the negative 5/4. So stare at this problem a little bit. All right. Let's take a look at this example. Sine squared of x cubed. See what you can do with that. Sine squared of x cubed. How many functions? Nope. Aha. 3 functions. No coffee. Very good. The first one, the outer one, is x squared. What's the one inside? Sine x. And what's the one most inside? X cubed. All right, so now this is this skill. I mean, believe it or not, this solves like 90% of the problem when you get something more complex. Your ability to decompose this into multiple layers. All right, so let's go. So yeah, this is my rule. It's the reason why I put this as skill. It's a multi-tool, okay? So, the whole sine, well, first of all, this x cubed is buried within the sine. And this square is the most outer layer for everything. So now, once you decompose, it is good practice to say, okay, let me just plug this for this x. Oh, great, I got sine x cubed. Now let me replace this x with sine x cubed, and you get sine x cubed everything squared, which works with that. So it's good to every time check this. Once you have this, the rest of the derivative should flow. Obviously, if you don't know the rules for differentiation, you're doomed. But if you do know rules of differentiation, it should go smooth. So what's the derivative of x squared? It's 2x. So 2 sine x cubed, right? You have to have everything plugged in. Times, what's the derivative of sine x? Cosine x, but I have to use x cubed. And then times 3x squared for the derivative of the one at the bottom. For the grand total of 6x squared sine x cubed cosine x cubed. Now there is a way to compress this for those of you, more vicious. You don't have to transform this, but 2 sine cosine, this part over here, that's a double formula, which is sine of 2x, right? So this whole thing is actually 3x squared sine of 2x cubed. That's what it is. Now, what is the first one? The first one is the derivative of f. Well, it's better this way. F prime of g of h. And then this guy over here is g prime of h. And this guy over here is h prime. To put this in the Leibniz notation, the derivative of the function in respect to x is df dg times dg dh times dh dx. Now I hope you see what happens when you cancel these. You get your df dx, which is what you were looking for. It's your first example with 3 functions. Right? Who's excited? Oh, thank you. Okay, ready for fun? Let's go. What is the derivative of cosine of cosine of, okay, of cosine. Good enough? Okay, good. Of square root of x. Yeah, I mean, you know. Need to make sure that people are happy, because your happiness is our primary concern. Here at United Airlines. You know what happens if you get out of line, though. Yeah, every night or two. Oh, you tried to see your child? Landing it out. Man, your baby's fine. You have test on it. How is the testing? The testing is in this place. Is it popular subject? I like the sound. Good.
Waiting for those calculus students to come out of exam. Calc 2. Yeah. You generally go, you see the first calculus exam, and then it goes down. Nothing to worry about. Nothing to worry about. We started slow and I tried to
All right. How many functions?
4.
4 functions. We have f cosine x, g cosine x, h cosine x, and what's the designation for this one? What did you pick? Z root x. All right, let's go. So we start by the derivative of the outer function. Cosine is negative sine, and then we have to have the cosine of root x. Good. Times. Then we are the next one in, which is technically this one. That's another negative sine of cosine root x. Then times, and I'm just going to put negative 1 over here so it's better. Times, then we're here, which is also negative sine of root x. And finally, 1 over 2 root x. There we go. So now negative times negative, that's 3 negatives, so altogether negative. And there is really nothing you can do over here. So sine, cosine of root x times sine of cosine root x times sine root x, everything divided by 2 root x. Oh, that's so cute. Look at that. You're gonna love this problem. The derivative of, it's not a trick, don't worry about it. It's the square root of x plus square root of x plus square root of x. Next one, someone is trying to make a point. Tell them to first decipher this, and then they can make a point. What? 4? Let's, you should decompose this on a paper and then follow the steps back to make sure it works. Let's see. Never get it. Well, it's too late. I mean, that has to be what do you call it? The custom, the entry for that. He's a whole. I'm in a bad track. No, I just didn't buy my ball. You had so much of your stuff earlier. That's terrible, right? Horrible. All right, so when the stuff gets stuff, you can work your way back. You see, there is a square root function of stuff over here, right? I don't care what that is. So I'm going to say that the outer function f is going to be square root of x. That's the outer function. And then I'm going to go one step inside and see that this is x plus another square root of x. Very good. And then age, oh no, that's wrong. You can't do this, because now if this one is a square root of x, then that's a problem. Alright, so you see that the method that we used before doesn't work on decomposing functions. This is really tricky. So what now? Now, you would say, well, now obviously we quit. No. So this problem, to take the derivative looking at this is not going to be pretty to write. Let's see if we can deal with the derivative in a logical way without actually writing the decomposition. I have the square root on the outside. I know that the derivative of that is 1 over 2, the square root, and it has to have all of the components of the inside. And now I have to take the derivative of the highlighted part. I have to take the derivative of that. Well, that's not a problem, hopefully, because the derivative of x is 1 plus the derivative of another square root, which is 1 over 2 square root of x plus root x. So how far did you get now? Well, you got far up to here. What's the derivative of that? 1 plus 1 over 2 root x. If I had that ta-da button. Ta-da. Oh, disappointed? Maybe I should toss in a secant, just for you, on the next exam. Yeah, I'll give this problem, but replace one of these x's with secant x. You'll be good. Oh, this one is fine? Okay. Yes. Yeah, I did, because it was tricky. Now let's try again. F of x is equal to the outer function is just square root of x, right? So for the square root of x, what's the inside? So g has to take everything that it's on the inside. Now, if you take a look at everything that it's inside, it becomes x plus the square root, but you can't put x here. That's the problem. Because this x and that x can't be the same. So if I put age of x over here, then the next one is age of x, and age of x is equal to x plus root x. But now the function composition that we used to love and like it doesn't look the same as previous examples because of this age of x over here. So now you can see that you can replace all of this inside the square root over there, and then all of this g instead of the x in there, and then it will work. But as I said, it really looks awkward. Now, square root of x, this is technically square root of g over here. And you see that g depends on age, and there is age that is just these two guys on in the middle. It's x plus root x. You have to understand that x plus root x is actually basic. That's the basic derivative. Because we know that the derivative of x is 1, and the derivative of root x is just 1 over 2 root x. So those are basic derivatives. So the whole thing over here is basic. And that's plugged into the square root, and that's plugged into another square root. So that's why we have the square root, that's the middle one. That's the one that has age under it, because this whole thing is age. So root of age plus x. So it's very tricky. So some of these problems are tricky to kind of decompose and write these, write the rules. What else? Ooh. So what is the derivative of the square root of 1 plus cotangent squared x? All right, so where do we start? What's F? Square root of x, okay. And then what's G? 1 plus x squared, okay. And what's H? Cotangent x, good. Wow, that's a lot, right? All right, so what do we do now? Don't worry about it. So what do we have here? The derivative of square root of x is? Exactly. So we have to put 1 over 2 square root of 1 plus cotangent squared x times the derivative of 1 plus x squared is just 2x, which is 2 cotangent x times, and derivative of cotangent is squared. Good. So now we can cancel some stuff over here, right? And hopefully make it better. So what do I have? I have negative cotangent x cosecant squared x divided by the square root of 1 plus cotangent square x. Good? Might be able to do more. The derivative of the square root of 1 plus cotangent squared x. By Pythagorean identity, 1 plus cotangent squared x is the cosecant squared x, and then the square and the cosecant cancel, and we have the derivative of the cosecant x, which is negative cosecant x cotangent x. Yeah. I gotta bring my glasses. I mean, it worked for the effect, but they cancel. Oh, that's a square canceled. The square canceled with the square root. Which means that the upper expression needs to cancel into this, which is 2 steps. Over here, the square root and the square would cancel. Would this thing on the top work? Of course it would. Look at your denominator. square root of cosecant squared x, and you have negative cotangent x cosecant squared x. So when these cancel, you get the cosecant, and then the cosecant cancels with one of the cosecants, and you have negative cotangent cosecant. Oh, works. Every time, 100% of the time. But that was the boss move, right? Against the glasses. Thank you. Good. All right, enough of easy problems. Let's take a look at something more interesting. What other techniques do we know for taking the derivative? Anyone? Which one? Say it. Quotient rule. Okay, great. You want to start there? Awesome. So now we can unite the chain rule with the quotient rule and the product rule. We can have a chain in a quotient, quotient in a chain, chain in a product, product and chain in the quotient. We can have all of these on a pile just because we can. All right? You said you want to start with a quotient, so okay, fine. So what is the derivative of a to the x squared plus 1 divided by x cubed minus 9x? So what is the part of this problem that makes it new and more advanced than just a quotient rule? What is the exact thing? There is one thing that makes this more advanced than what you did 3 weeks ago. Yes.
X squared in the exponent?
Yep, the squared in the exponent. Yep, the x squared. If that was e to the x, this would just be the very basic, everyone should know it by now, quotient rule. But it's not e to the x. It's e to the x squared. And that's what makes it a chain rule right there. Now the problem is still a quotient rule problem. But when we get to the point to take the derivative of the numerator, then the chain rule kicks in. So this is chain within quotient. All right, we can do this. What's the quotient rule? Take the denominator, copy it and square it. Take the denominator and copy it again. Times the derivative of the numerator, this is where the chain rule kicks in. The derivative of e to the x squared plus 1 is e to the x squared times 2x is a chain. The derivative of plus 1 is 0, so we don't have to worry about that. Minus, from the formula, e to the x squared plus 1 times the derivative of the numerator, which is 3x squared minus 9. Yeah, there it is. Beautiful, right? Are we going to simplify this? No. Why? Because future. All right? I will tell you I'll tell you next Thursday. Right now I'm just saying you don't have to simplify this. Go ahead, you can FOIL everything, sure, why not? But yeah, for now we don't need to. All right, let's find another derivative since you love this stuff so much. Let's just put a basic wave, right? Let's just put a wave. So e to the negative 3x cosine 5x. Standard stuff. So this is a wave, like the oscillator that with dampening. So it does this. And it dies out. Terrible line. Whatever. Trying to draw the x-axis and I'm not succeeding. There it is. So when you leave something, let's say if you hang a pendulum at the ceiling, oh, welcome to differential equations, by the way. Suspend the pendulum from the ceiling and just smack it. It's going to start doing this. Is it going to do this forever? No. There's air resistance, there's gravity. So those two things will slow it down. So the amplitude will be the largest in the beginning, and then it will slowly, it will stop. So this function measures the displacement from the highest amplitude to one side, the amplitude to the other side, right? So it measures that displacement to the other side, and then it gets smaller and smaller and smaller and smaller and smaller and smaller and smaller, and then stops. So that's the mathematical function which describes it. And it's a solution to some of your differential equations. Now you have to take the derivative to check it. So this is some standard stuff for diffq. Now these happen to be two very simple chain rules within a product. You know both of these formulas off the top of your head, so you can quickly write this. But then there are some more interesting examples that will be harder to deal with. So what is this? It's a product rule. And if it's a product rule, we have to do the entire product rule formula. This is U, this is V. So copy U times derivative of V. That's negative 5 sine 5x plus copy cosine 5x and take derivative of the other one, which is negative 3 to the negative 3x. So what you can kick out is negative e to the negative 3x, and what you're left with is 5 sine x plus 3 cosine x. And that's the answer. So this was chain within product. U, V prime, V, U prime with the plus in between. Right? That's the formula. UV prime plus VU prime Copy the first, derivative of the second, plus copy the second, derivative of the first. And then you just do some algebra to factor things out. Why do I have this x over here? Good. Are we done? No! There is a second derivative to be had, and the third, and the fourth, and the fifth. Small break. All right, then part 2 when you come back.